In the last lecture, we talked about the energy levels of atoms, and in particular of the hydrogen atom. We know how much energy there is in each of the energy levels in a hydrogen atom. In this lecture, I'm going to talk about how electrons can move between energy levels. And I'm going to continue to focus on hydrogen. Again, that's just the most common element in astronomy, and it's also the easiest one to deal with. So you can see here I've redrawn the energy level diagram for hydrogen. I labeled the levels for the ground state and so on up. And we can remember that the ground state has an energy of 0. If we get more than 13.6 electron volts of energy, the electron leaves the atom and we become ionized. I've also put in an electron this time. Now, I've started off with the electron in the ground state. That's generally where you're going to find it in most hydrogen atoms. Electrons like to have as little energy as possible, so they like to try to end up in the ground state. The ground state has no energy. Well, how do I get an electron from here up to the first excited state, or even higher? It's got to get energy from someplace. If it wants to move up, it has to gain energy. To move up in level, it has to gain energy from someplace. It can't just go from 0 to this one's 10.2 volts just magically. It's got to get energy from someplace. That's conservation of energy. Energy is just not created. It has to get energy from someplace. Similarly, what if it was up here in this excited state and it wanted to move down? Well, up here it has more energy than it would here. So to go from here down to here, it's got to lose energy. To go up in level, an electron has to gain energy. To go down in level, an electron must lose energy. So the question is, where can we get energy from if we want to go up in level, or how can we get rid of energy if we want to go down in level? And you might want to think about that for just a minute. Now, maybe you have thought quickly about the other thing we've discussed in this course that has energy, and that's light, or photons. Photons have energy. And this is where electrons can gain energy from, and it's also how they can get rid of energy. If we have a photon of just the right amount of energy, to go from here to here, it requires 10.2 electron volts of energy. If I have a photon that has exactly 10.2 electron volts of energy, the electron can absorb that and it can jump up in level. Or if it wants to go down from here to here, it can get rid of 10.2 electron volts of energy by giving off a photon of exactly that amount of energy. So the way we have transitions between energy levels is by interacting with light, by gaining or by absorbing or giving off photons. The key thing is the photon has to have the right amount of energy. So if I want to move up in level, to go from here to here, here I have 0 energy. Here I would have 10.2 electron volts of energy. To go from the ground state to the first excited state, I would need to absorb a photon whose energy is exactly equal to 10.2 electron volts. To go from 10.2 to 12.1, from the first excited state to the second excited state, I don't need 12.1 electron volts of energy, I need 1.9, because I've already got 10.2, so to go up another one, I would need 1.9. If I wanted to go from the second excited state all the way down to the ground state, I would need to get rid of exactly 12.1 electron volts. So I would need to emit or give off a photon whose energy is exactly 12.1. If I were in the second excited state and I wanted to get ionized, I would need to somehow gain more than 1.5 electron volts, because if I get exactly 13.6, I'll be at the ionization level. If I get a little bit more than that, I can be out of the atom completely. So by absorbing a photon whose energy is enough to take it beyond 13.6, I can create ionization. but for any transition within the atom, the energy that is going to get absorbed or emitted has to be exactly equal to the difference between two of the levels. To go up from the first excited to the second excited, I have to absorb 1.9 electron volts. To go down, I need to emit 1.9 electron volts. Now, I've been dragging my electron around here, and you sort of see it moving through this space in between here. But it's an interesting little fact. Remember, it's not allowed to be here. It would have the wrong amount of energy. It can only be here or here. It can't be anywhere in the middle. So when I'm dragging it through here, that's actually a misrepresentation. It does not travel through this space right here. It's here, and then magically the next instant, it's here. It actually teleports between levels. It does not pass through the space in between. This is what's called a quantum leap or a quantum jump. It's a transition from here to here without traveling through the space in the middle. So that's why you hear a lot about quantum leaps or quantum jumps in science fiction stories, is because you're going from one place to another without traveling through the distance between them. This is a figure from your book, and this is just a good one to review. There's going to be several problems that we do that relate to this. So again, this is the energy level diagram for a hydrogen atom. And we're going to imagine, at least starting with a few of them, down in the ground state. If a photon comes along and has 5 electron volts of energy, the electron is just going to ignore that. It can't take 5 because 5 would make it end up between two levels. It's not allowed to take that 5. The 5 is just going to go on its merry way and the electron will ignore it. Same deal with 11. If this electron gained 11 electron volts of energy, it would end up here between level 2 and level 3. It's not allowed to be there. It can only be in exactly one of these levels. So it's just going to ignore that 11 electron volt photon, and that one will just go on its way. However, if one comes along that has exactly 10.2 electron volts of energy, then the electron will absorb it and jump up to level 2. Now, what about once it's in level 2? Well, suppose that it gains enough energy, like say more than 3.4 electron volts, let's say it's something like 11, then its total energy would be 21.2. That is more than 13.6, so it will escape the atom. It can absorb anything that is great enough to take it above the ionization level. And it doesn't have to be 13.6, it would just have to be more than 3.4 to get it past the ionization level if it's already in the level 2. Similarly, if it's in level 2, it can emit a photon of 10.2 electron volts and drop back down to 0. It's not going to emit a 5 electron volt one or anything like that because that would make it end up somewhere in the middle. So these are all, this is a legitimate transition, this is a legitimate one, and so is this one, but these two are never going to happen. Now, I'm going to talk about how we're going to do some problems with this real briefly, and then in the next half of the lecture, we'll do some examples. The key idea is that the difference between the energy levels that we're jumping between has to be equal to the energy of the photon that causes the jump. So you may want to pause and just write down this procedure. Here's what you're going to do. You're going to first off have to find the energies of the two levels if I don't tell them to you. In hydrogen, you may just know them because we've done them so many times. If it's anything other than hydrogen, I have to tell you the level. But it might be two levels in hydrogen that we haven't done. Like what if I tell you between levels 7 and 8? Then you might have to calculate the energies of the two levels. Then you're going to subtract them. We're going to call that delta E. That's the difference between the two levels. Like between level 2 and level 1, it's 10.2. Between level 3 and level 2, that's 1.9. That's 12.1 minus 10.2. And this energy is equal to the energy of the photon. So since that is the case, and we know that the energy of the photon is equal to HF, that's our formula for the energy of a photon, I can set that delta E value to HF, and I can figure out the frequency of the photon. And then if I want to find the wavelength, I can plug the frequency into v equals lambda f. Of course, these are particles of light, so they travel at the speed of light, and we can solve for the wavelength. So this is how you're going to do problems involving these transitions. Key thing that we're going to need to know is that for any given element, the energies that work and the wavelengths that correspond to those energies are unique. The set of wavelengths that you get for hydrogen is completely different from the set of wavelengths you get from helium. And that's completely different again from the set of wavelengths you might get from oxygen or nitrogen, carbon, anything like that. Every element has its own unique set of energies and wavelengths. And that's going to be very important to us when we want to find the composition of objects in space. I'm going to stop now and switch to the next video to do some examples. So this is the end of the notes part, and then we will do some examples in part 2.